we can kind of start to walk through what this lab all entails. So first I have my introduction here where I give you like just kind of a background about computing and spreadsheets and where that really comes from. And I feel like this is really helpful for us to really understand what we're looking at when we look at the spreadsheet. Basically, a long time ago, before there were ever computers, there were these things called spreadsheets, and they were exactly that. They were a big sheet of paper that you would spread across a table, and they had all these little boxes in them, and people would use that to kind of organize their calculations back when they had to do them by hand. And this became the analogy when we started to move that work over to computers. It was a familiar sort of uh, analogy for them that they could people could kind of wrap their heads around. Uh, that said, it's not the best way to organize your math by any means, and nowadays we're pretty far removed from using a big giant sheet to do our calculations. So if it ever seems confusing why it's like that, just know that it's just an old thing that got carried forward. The second thing we want to talk about is the difference between local applications and web applications. And I think that this is something that really confuses people a lot of the time. Local applications are the applications that are on your computer. So if on my computer, if I come down here and click on my menu here, these are all the applications that are installed on my computer. Now, if I go and use one of those applications to generate a file, that file stays on my computer. Okay. There's issues with that though. You know, it may not, the application may not work the same on my computer as it does on your computer. And oftentimes, especially in the case of things like Microsoft's products, you're going to have to pay for those applications. The other thing that you can use is going to be a web application. A web application exists inside of your browser. This is the browser is an application that's on your computer. The web applications exist inside of them, and you're going to interface with them through one of the tabs on your browsers. This is a web application. The most important thing for you to realize is that when you generate a file using a web application, it's not on your physical device. It's still on a server somewhere that you connected to show you this web application. And both of them have their pluses and minuses. If I use a local application to generate a file, well, if I want to share that file with people, I have to have an additional step to go and do that. I have to share it with people as an email attachment or upload it to some sort of drive somewhere for them to be able to see it. When I go to another computer, I'm not going to be able to access it. Now, if I make an app, if I make a file with one of these web applications, well, now it's on a server, and I can go to that server, and I can retrieve that file. That said, I have to understand a lot of things to be able to retrieve that file. For instance, here in the case of the Google Suites, I'm currently logged in as michael.stockstill at mcc.edu. If I logged in as any other person, if I just picked up somebody else's computer and maybe I didn't remember my login, or I didn't understand that I needed to log in as myself, I would never be able to access that file again. There's also the idea of privacy. The server owns your information now, and it can do with it whatever it wants, including just deleting your file. Whereas if it's only ever on your computer, you are always in control of it. So I'm not advocating for one over the other, but we do need to understand the differences Because we're going to be using a web application today, you are going to need to do the assignment, download a file, and then share that with me. And I'm going to show you exactly how to do that once we're done today. There are a lot of options for different spreadsheet programs. Probably the most famous one is going to be Excel. That is a Microsoft product. And confusingly, Excel now exists both as a local application you can put on your computer and as a web application in the form of what they call Microsoft 365. You can gain access to this for free through the Microsoft Corporation if you go there and give them your .edu email. They allow students to use it for free for some amount of time. After that, though, they're going to ask you to pay for it. Now, Google Sheets is always free. It always has been free, and just a part of the Google Suite, Gmail that you may have already, a personal one, and the one that you were given by Mott. They make their money by selling upgrades to this. So, for instance, there may be features that you can get into in the Google Suite at Mott that aren't available on your personal Gmail account. If you went to another corporation who was using the Google Suites, they may have access to other features that Mott doesn't have. One thing I do really want you to take a look at, I think that this is very useful to people, is LibreOffice. LibreOffice is an alternative to Google Sheets and Microsoft Excel. It is free. It will always be free. And you can install it on a Windows machine, a Linux machine, a Mac OS X machine. It does not matter. They have them all. And it has replacements for all of the Microsoft products. Word, Excel, the presentation software and stuff. You can even do some drawing and some basic database management with it. Not all of these options are going to work on all devices. Specifically, the Google Chromebooks, you're really going to be limited with the software that you can have on there. If you're using Windows, a laptop, or a desktop, you have your option between Excel, LibreOffice, OpenOffice, which is another alternative that's not quite as good as LibreOffice, or Google Sheets. You have on an Apple, you have Excel. Numbers is the Apple's version of Excel. You can install the LibreOffice or the OpenOffice. On a Chromebook, you're typically going to be stuck with using either Google Sheets or possibly, depending on your device, CollaboraOffice, which is basically a web application that is done by LibreOffice. So the first thing that we need to realize is that we're not at Mott today, so we can't exactly follow these exact things, but I have already shown you how to actually get to Google Sheets. The first thing I'm going to do is I'm going to increase the zoom here to make this a little easier for you guys to see. I did that by clicking this drop down and just choosing 150%. The next thing we need to understand is a few things about the way that we can manipulate things inside of spreadsheets. So each one of these little boxes is called a cell. If I click on a cell, it's going to highlight it. If I click on a cell and continue to hold down the left mouse button and drag, I can drag a section of cells. If I click this header here, it's going to select all of the cells in this column forever. This just goes on infinitely. If I clicked multiples of them across here, I can highlight all of these sections down forever. If I click here, I'm highlighting this entire row over again for infinity. If I highlighted multiples of them, I'm highlighting all of those cells over here for infinity. If I wanted to resize this column, say I wanted to make this column wider, I would click up here to highlight that. I would go to the edge here where I now have that double-sided arrow, and I could move the entire thing. If I wanted to make the first 4 columns here, A, B, C, and D, all the same size, I can highlight all 4 of those columns and just move one of them. That's going to resize them all to be the same size. If I click right here, I'm highlighting all of the cells, all of the rows, and all of the columns forever. And I can resize either these or the rows by coming to the edge here and resizing them. Now that we have kind of got the navigation down a bit, let's talk about what we're going to put in our cells. The cells can take 3 different types of inputs. You can have a string or a word, which is exactly what it sounds like, a word. You can have a number, which is again exactly what it sounds like, a number. You can notice here that the word was left justified. It's pushed over to the left-hand side of the cell. This is what Excel and any of these spreadsheets programs are going to do, assuming you haven't already done any kind of formatting to prevent it, in order to indicate to you that it recognizes the input you put in there as a word. Here, it's right justified. It's pushed over to the right-hand side of that cell. This is Excel's way of telling you that it recognizes that as a number. One of the big problems students start to get into in this class is that they, out of the best of intentions, want to input both a number and a unit. When you do that, though, you can see that Excel pushes it to the left side of the cell. It is operating as if this is a word, just like this one. And it's not going to allow you to use that number, 13, to do any math in the future. Instead, it's just going to throw some cryptic errors at you that may get frustrating. So, if we intend for a cell to hold a number, it can only hold a number, and you cannot put the unit on there. We do need some sort of way of indicating the unit, though. And you're going to see that the way we're going to do that is by placing that unit into an adjacent cell where we're going to indicate the unit and what the quantity actually means. So we're going to have labeling cells as we continue. If I highlight these 3 cells and push the delete key on my keyboard, I can get rid of the stuff that I added in there. Remember that I said that Excel is going to accept 3 different types of inputs. So far, we've seen words and numbers. But if that's all it did, well, all it would really be is some sort of kind of gridded note-keeping feature. The big thing that you can do in Excel is be able to input actual math equations, similar to the way you would enter them into a calculator. Now, what you have to do, though, is indicate to Excel that you're inputting some math first. It doesn't presume that you are inputting some sort of formula like a calculator would. The way you indicate that you want to add a formula is by first hitting the equals button. You're telling that cell that you want it to equal something. For instance, I could say that I want this cell to equal 12 times 3. Notice I'm using the asterisk for multiplication, similar to the way you might on a calculator. If if I hit enter, we'll see that it does not show me equals 12 times 3 anymore, but instead the answer, 36. Now, this is usually the desirable thing that you want to have, for it to show you the output of the equation that you entered. Sometimes, though, you want to see all of your equations instead. The way that you can do that in any of these spreadsheet programs is by holding down the control button. You'll find that usually on the bottom left or bottom right of your keyboard. It's often abbreviated CTRL. And then pushing the tilde button. The tilde button is that mysterious button to the left of 1, above tab, below escape. If I push that, it will start to show me just the equations and not their outputs. If I want it to go back to the way it was, I'll hold down Control again, and I'll press the tilde button again. I can now easily toggle between the two views. So that brings us up to about here. It's important to note that order of operations still holds the same way it would for a calculator. For instance, all three of these expressions give us a different output. This one is 4 plus 2/3. First, it's going to divide 2 by 3 and then add it to 4. This is 4 divided by 3 plus 2. 4/3, 1 1/3, plus 2 is 3 1/3. This one, I've now specified parentheses. It's going to do the thing inside the parentheses first. 4 plus 2 is going to be 6, divided by 3 returns 2. So do not get confused with this inline notation. It's the same sort of issue you may have with a calculator. Remember, parentheses are your friends. That is how you explicitly tell your calculator and Excel exactly what math and what order you want it to do. Now, if we come in here and say that this cell is equal to 1/3, you can see that we have the classic dilemma here. This is a repeating decimal that goes on forever, and it has randomly chosen to just fill that cell with 3s for you. We know from our studies that we want to represent numbers like this with the appropriate number of significant figures. We also know that significant figures do not come from a calculator or this Excel sheet. We need to tell it explicitly how many significant figures we want this to show. The way you do that in Google Sheets isn't great, but what you do is you come up here to Format, and you're going to see that there's this number section here. And it gives you a number of choices with some representations down here of exactly different number formats you might choose. The problem comes when you don't want one of these choices. For instance, this one's going to show me 1 decimal place, 2 decimal places, 3 decimal places. What if I wanted 4 decimal places? Well, you have to come down here to what we call custom number format. If you click that, you're going to get what appears to me to be a fairly confusing sort of notation that they want you to use. You see that you use these zeros to kind of indicate what format you want the number to take on. For instance, here, if I wanted 4 decimal places, I would need to add 4 zeros. Now it will represent the number much like this with 4 decimal places. I can click that and hit apply. I now see my value with 4 decimal places. It is best to always do this when you're trying to do your formatting in Excel. Here's the other thing. Now that I have formatted this cell, it has a memory. It's going to remember that it was formatted that way. If I put in some sort of other repeating decimal, it is going to format it to being 4 decimal places. So now that we've learned about inputting values and formatting them to appear the way that we want to, the next thing that we're going to want to talk about is going to be scientific numbers. There will be times when we want data shown to us as a scientific number, and there will be times when we want to enter scientific numbers into a calculator or into Excel. Now, this can be kind of burdensome. In a typical calculator, you might want to represent this number here in this fashion: 1.00 times 10 raised to the power of -5. The problem is, this is not the best way to input that number. As a matter of fact, anytime you put a number like this into a calculator or into Excel, you should always protect it on either side using parentheses so that the calculator knows to treat it as if it's one number. Otherwise, you're quite likely to run into an order of operations problem. In order to work around that, calculators and spreadsheet programs for a long time have had what they call exponential notation. Here, what we do is we replace the asterisk, the 10, the caret, with just a single character E. Originally, E was used because you could generate an E symbol using the old school LCD displays you might see on a calculator. And they just happened to say E for exponent, and it all kind of worked out. This is the most desirable way to represent these numbers. So if I had a scientific number that I wanted to input, like say Avogadro's number, 6.022 times 10 to the 23rd, I would go to this cell and I would type in 6.022 E23. When I hit enter, you can see that it has already changed that to be in the format that I specified before with 4 digits. If I want instead for this to be shown 4 decimal places, if I instead want this to be shown to me as a scientific number, I can choose to do that. I would come up here to format, I would go to number, and I would choose scientific. You can see next to it that they are using the same E notation. And it's going to give it to me in that E notation. I could have just easily as gone to a cell and just typed in a really long number. If I wanted that expressed in scientific notation, I could do the exact same thing. I could go to Format, Number, and choose Scientific. It's now showing me it in scientific notation. If I wanted to come down here to Custom Number Format, I could come up here and add an extra 0 or 2 here to add to the number of decimal places that it shows me. It would work equally well for a really small number. If I put in a small number, I could come up here to format, choose scientific, and if I wanted to see more of the digits, I could come back to number, come down to custom format, and just add a couple more zeros here. So now we can format these in either scientific or regular notation. We also learned something important. We learned that these cells have a memory. Now that they have been formatted in scientific notation, if I delete them and then input a new number, it is still going to be in scientific notation. To varying degrees of success, you should be able to highlight all of these cells, go to format, and clear that formatting. In my experience, Google Sheets sometimes just simply won't do it though. But you can always come back here, go to number, and just go back to automatic, in which case you'll still be back to the condition that you were originally in and the way that it would default to showing you numbers. Now, if all we could do is input words, input numbers, and input equations like I've shown you so far, these spreadsheet programs would be no better than a note application mixed with a calculator. The real power to Excel and any of these spreadsheet programs is the ability to reference other cells in your equations. What do I mean by that? What I mean is that if I were to have a cell here that I input a number into, and another cell here that I input another number into, and let's say that I want this cell to be the product of these two. Well, I could put in equals 23 times 487. Or I could go back to it and say that it equals, click on this cell, in which case it propagates there a reference to that cell. That cell is cell A1, and I could say that I want A1 times this cell B1, and it will return the exact same result. Why is this the superior method, you might ask yourself? Well, now if I go back and change the value of B, it automatically is going to update this value C here. If I double click on this, I can get back to this condition. Notice the highlighting that's happening here. This is gold trimmed with a gold lettering on there. Purple with purple lettering. It's trying to indicate to you which cells it's referring to. Now, had I not wanted to do the clicky thing, I could have just as easily as put in A1 times B1, and it still recognizes what those cells are and does the highlighting for us. I didn't even need to make them capitals. We can use this to make a lot of repeated calculations quite a bit easier for ourselves. Let's say that we have some random data here. And I want all of these cells to be the product of these two all the way across. I want to reproduce this cell down here. What I need to do is first look at the cases when I put my cursor on the cell. You'll see that if I put it directly on the cell, I get a regular arrow. This is indicating to me that I can highlight that cell. I can double click on that cell to view and edit the equation that's in there. If I instead put it down to the edge, any of the edges, I get a grabby hand. What grabby hand is indicating to you is that if I hold down the left button to grab it, I can now move this cell around. Notice that it keeps its value when I do that. Now, here there's a little dot in the bottom corner of this cell. If I put my cursor there, I get these crosshairs. If I hold down the left button and then drag down, we can see that what it does is propagate all of the cells beneath it with that same equation. But it's not quite the exact same equation. This one is A1 times B1, but when we came down here, it's A2 times B2. Excel knew that I wanted to increment both of these as I dragged down. And you can see that it continued to do it as we went along. Most of the time, this will be the desirable thing that you want to do. This is going to help you from having to type in a lot of the same thing over and over again. Sometimes, though, you may want to add something or do something with this where you want to work with the same number each and every single time. Let's think about that. Let's say that to each one of these, I wanted to add 10. The most natural thing to do is to come over here, say that this cell is going to equal that cell plus this cell over here. And that worked out just fine. We went from 12,029 to 12,039. Let's see what happens when we drag it down. When I drag it down, it first off gave me a little suggestion right here. It said, do you actually want C1 plus G1? But instead we're putting these little dollar signs in front of the G and in front of the 1. What that is indicating to you is that you are probably making a mistake, and it is trying to save you from that mistake. I want to show you what the mistake is, so I'm instead going to click X here and reject its suggestion. If I go here and click on it to look at my highlighting, I see that it's taking C2 as I intended plus G2, an empty cell. And what it's returning to me is the exact same number. It thought that you wanted to continue down just like you did in this case. To prevent that, you do exactly what the suggestion it gave you was. You place dollar signs in front of the values you do not want to change. A dollar sign in front of G will make sure that it always is referencing the G column. A dollar sign in front of 1 means that it will always reference the 1 row. It will never change those values. Putting dollar signs in front of both means that you will always be referencing the exact same cell. In this case, G1. If I drag that down now, we can see that it is now doing the correct thing and always adding G1 to each and every one of these. Now, Excel has a whole bunch of built-in functions. Let's say here, we can already see that we are actually making this kind of complicated, so we should start to add some labels. Let's call this the X, let's call this the Y. We're going to call this the x times y. And we're going to call this the x times y plus g1. Let's say that I wanted the average of this column. The thing you might think to do is to come in here, open a parenthesis, say I want this one, plus this one, plus this one, plus this one, plus this one, divided by 5, because I have 5 different values. And I will get the average. If I remember to use my division symbol, I will get the average. Now, if I had hundreds of these, this would be prohibitively difficult. Instead, we can use built-in functions that Excel has. For instance, instead of saying I want this one plus this one plus this one, we can actually use the sum function. All Excel functions are going to be labeled with the function name. After that, you're going to see a pop-up often that's going to give you the various functions you can choose. Typically, in this case, you would just want sum. And if I click that, you can see what it's going to do. It's going to open a parenthesis. So I start by naming the function and opening the parentheses. I could then click the ones that I want to add, placing commas in between each and every one of them. But this is still bad and prohibitive, honestly. It would be nice to have a way to specify all of the cells between D2 and D6, and we can certainly do that. The way you would do that is instead of using a comma, we use a colon. You can now see that it's highlighting D2 all the way to D6. I could have gotten the exact same result by starting with the empty formula, highlighting the first cell, and dragging down. Once I'm done and satisfied that I have done what I needed to do, I can close those parentheses there and then divide by 5 to get my average. This is still not a very desirable thing to do because I'm still required to figure out how many of these I have. In this case, I have 5. You do not want hard-coded values like this inside of your functions. That is going to make it difficult for you to edit your work later. Instead, you want to be sure that you're always using the correct function to return the value that you want. In this case, I shouldn't be using the sum function. I should be using the average function that is built into Excel. If I open the parentheses now, I can highlight all of these values, close these parentheses here, and I get the average of those values. Now, I've shown you the sum function and the average function. But what if I didn't know which functions were available to me? Well, I can click up here on this little sigma here. You can see that it says functions beneath it. And I can choose all of the various functions from these lists. It is not a bad idea to look through these and see which functions are going to be pertinent to you. I will be showing you the ones that are going to be used to solve our work today. So let's say that we had this data here. The first thing I really want to emphasize to you guys is that because this is a web page and this is a web page, I'm going to be able to highlight this data here, hold down Control-C and simply copy it like that, come over here and then paste it into, golly, wants me to Control V instead and paste it into here. It even retained quite a bit of my formatting when I did that. This would not be true from a regular Word document necessarily, and certainly not true from a PDF. Now, if we look at this, we can see that this is a measurement of the air pressure of the tire inside of our car, the same tire, over and over again. So we made 5 measurements. Each of them was slightly different. What we want to do is to figure out what this data is telling us. What is the most likely pressure inside of the tire, and how bad is this data? How much do these points deviate from one another? In order to do that, we're going to need to use statistics. The central tendency of this data is going to be the average. If I want to show the average, I'm going to start by making a labeling cell that says that the cell next to it is going to equal the average. I can use the average function, highlight these cells, and return that average. This is the central tendency of this data. It is the number we would expect to get to, or at least close to the number we would expect to get to, if we continue to take measurements of this data. The second is called the standard deviation. The standard deviation is a difficult little equation that I have spelled out in next week's lab, and we can talk about it. But I'm not going to ever require you to calculate the standard deviation by hand. Instead, I think it's best for us to use Excel to do this calculation. The higher the standard deviation, the more these values are going to deviate from the average, meaning that the quality of this data is poor. The lower the standard deviation, the less these values deviate from the average, meaning that the quality of this data is high. To calculate the standard deviation using a spreadsheet program, we're going to say that this cell equals STDEV. We're going to open the parentheses, and we're going to select the exact same data that we did for the average. New students sometimes make a mistake here, and they will continue down and include the average in their standard deviation. This is incorrect and will return the wrong value. You want to have the exact same data, your plot points here, that you used in the average. Meaning that if I inspect the values here, both the average and the standard deviation are using the cells B2 through B6. If we continue on here, we need to build on one more important bit of information that we have here. In this case, I was measuring the exact same thing repeatedly. This is good practice in any sort of experiment. But there will come times when I want to vary a variable and measure an output. Here is an example of some sample data here. Typically, you're going to have x, a variable that you are going to control how it varies, and y, a variable that you will be measuring. Let's generate the same sort of data over here and see what this is going to look like. I'm going to do 1, 2, 3, 4, 5, and 6. Here, I'm going to do 5, 10, 15, 20, 25 and 30. I'm going to say that this first column is my X values, and this second column is my Y values. First thing I might think to do is to make a plot of this. Typically, the variable that you want to change, the X variable here that you're in control of, is going to be plotted on the horizontal axis, while the variable that you're measuring is going to be on the vertical axis. This can be achieved by setting this up specifically like this, with X on the left-hand side and Y on the right-hand side. In order to make this plot, the spreadsheet program makes it pretty easy for us. I'm going to start in the top left with just the numbers. I'm not going to come up here and grab the actual title. I'm just going to have the number section, and I'm going to highlight it from the top left to the bottom right, making sure that I highlight all of those values. Again, I did that from the top left to the bottom right. Some versions of some spreadsheet programs will return the same thing regardless of how you did that highlighting, but traditionally they have not. They make a very clear distinction between highlighting from the bottom right to the top left and the top left to the bottom right. You want top left, bottom right, left to right, top to bottom, just the way that we read in English. I'm now going to come up here and click Insert, and I'm going to come down here to Chart, and I'm going to click it. When I do that, it will start to generate the chart for me. There is a memory to this. The last chart that I made was a scatter chart, exactly the type that I want to make now. In general, though, if you haven't ever done this before, it will often default to the wrong chart, the last kind that you made, or a column chart. If that's true, you need to click up here to chart, column chart, and you need to come down here until you get to scatter, and you want to choose this image on the left hand side. This is going to give you the type of scatter plot that you will be making in our class. The next thing that you're going to want to do is to inspect this a bit. Does this graph look like what we expected it to look like? Are these X values plotted along the X axis, and are these Y values plotted along the Y axis? The first point would be 1, 5. If I look here, the 1 appears to be right here. This appears to be 5. That looks to be the point 1, 5. 5 on the Y, 1 on the X. And if we look at the scale here and the scale here, everything seems to line up perfectly. This is in fact what we were looking to get. That is pretty much all of the setup that you need within this part of the chart editor at this point. However, we are going to need to come over to Customize here to add the features that we're looking for. The first part here is the chart style, and I honestly don't recommend that you really change much about it at all. This is already probably about the most professional looking type of chart that you could possibly get out of Google Sheets. It's not going to give you a particularly professional looking chart, by the way. The next would be for your titles. You'll notice that there is still a bit of a memory here. This is the title that I gave it last time, and it's not really what I wanted. I would prefer for this to look like X versus Y. That is traditionally the way that this is always written. The X versus the Y. Meaning, if I gave this a different label, Like, for instance, if this was a distance and this was a voltage, I would write distance versus voltage, always in this x versus y fashion. This is going to give you probably the simplest, straightforward way of labeling a chart. That said, you could be much more descriptive in your choices of chart labels. I just don't have a lot of context in this example to come up with one. Notice that we lost the sidebar that we were working with. This can be frustrating sometimes, but can be recovered if we come up here to notice these three dots here and then go to edit chart. It will reopen that sidebar and drop us back to the setup tab. Let's go back to customize. We can see that we can customize the chart title. We can customize the labels on the various axes, and we can even add a subtitle if we're looking for one. This is essential and something you need to always make sure that your chart has. Without labels for the x-axis, the y-axis, and the overall chart, your data is meaningless. And the reason you made a chart in the first place was to communicate your data. So this is always a very poor idea to not include these elements and be as descriptive as possible. We're going to skip over series because that's probably the most important one that we need, and we're going to look at legend here for a second. You can see that this is just a way to theme your legend. We haven't added one yet, but it's only going to allow you to change the position of the legend and the coloration of the legend. We'll see later, it doesn't give us a lot of options for a real formatting of the legend, which is the thing that we would typically want that Excel and LibreOffice gives us. Here on the horizontal axis, you can see that you can change the text colors, you can change the font sizes. Sometimes you may want to make those larger, and you can change this default that it has here. For instance, I could say I want my x-axis to start at -1 and to go all the way to 7, in which case it has now reformatted the x-axis here. Notice that it does this better at some times than others. For instance, here it really wants this highest value to be an even value in order to show me this vertical dark line at 0, which is something you would want to have there. If you don't like that, the way that you've changed it, you can always get rid of these. If instead you wanted to format the vertical axis, you could always go to the vertical axis here. In the future, you may need at times to use a logarithmic scale. I'm not going to talk to you about logarithmic scales today, but know that this is a fairly common thing that we might do in science, and this is where you could do that. Now, if we look at grid lines, sometimes, especially if I want to make this large and do some sort of graphical analysis, I may want more than just these coarse grid lines. For instance, in the vertical axis, I have a fairly large spacing here. This is the numbers 0 through 30, where this is the numbers 1 through 6. I may want to have smaller increments for my grid lines along this axis. If I choose the vertical axis, I can go down here to what we call the minor spacing type. And I could choose step, just like this one. And I could choose a value for it, say 1. Now we can see we still have the major grid lines at 10, 20, and 30, but we also have these minor grid lines that occur every 1. So 1, 2, 3, 4, 5, 6. This would allow us to figure out how far and estimate in between these values. that is often a desirable thing to do. If I come back to series here, you really don't want to mess with the data series. Once this is looking like what you want it to look like, you may want to change aspects about the coloring and stuff, or the point sizes. For instance, maybe I want to have those to be smaller points. Perhaps I want them to be larger ones. But the default is typically king. I have found on occasion that I wanted to change the color of these points just to be more consistent with the document that I'm adding them to, and that is very easy on Google Sheets. The big thing that we want access to is this right here, specifically the trend line. What we often want to do is to find a line that best fits our data. Okay? Our points may not actually lie on a line, but we want to find the best line that could possibly fit the data within the error of our measurements. This is done mathematically using a technique called linear regression. It is a difficult bit of math to do. In fact, I know of very few people who would actually bother to do it. Instead, you do your linear regression using a program like Excel. In Excel, that linear regression that it's going to do is called a trend line. If I click here, you can see that it added the trend line in here graphically. That actually gives me very little useful information. I, as a scientist, need to know what the equation of that line is and how well it fits my data. If I want to know the equation of that line, I need to come down here and tell Google Sheets to show me that equation of the line. It's hidden underneath this label section here. If I click there, I can say use equation, and it will show me the equation of that line. I can click this box here, and it will show an r squared value. What is the r squared value, one might ask? Well, the r squared value comes from the linear regression math, and it is called the coefficient of determination, or r squared, or RSQ. An r squared value of 1 indicates that the points that you have there do in fact lie on the same line, as is the case here with this simple case where I just took each of these values and multiplied them by 5. I in fact do have a line that perfectly fits this data, and it would be 5x plus 0, where the y-intercept is 0 and the slope is 5. Now, what we're going to see is that an r squared value of 1 is the most desirable thing. However, as this starts to deviate away from a perfect line, that r squared value is going to start to go down. An acceptable r squared value is actually really high. You should not be working with data where you have an r squared value of less than 0.98 typically. That is usually our cutoff for saying that we have good data. You may design an experiment with a different criteria for your r squared, which may be acceptable depending on the type of work that you're doing. However, you should set up in advance of the experiment what an acceptable r squared value will be for you. This gives you an unbiased way of rejecting or accepting your data later. You can see also that as I change those values, the equation of the line changed as well. This is all well and good for graphically representing to a audience how our data operates. But this is still not particularly useful to us to work with. Number one, Google Sheets has chosen how many significant figures to show us and often makes very poor choices. For instance, these values here do not represent the type of significant figures we'll see when we are making careful measurements in the lab. It is really geared more towards somebody working in business or finance, where they would not want to see a long string of numbers there. Also, ideally, we want to have these values inside of cells. This would allow us to work with them later, to reference them, and be able to do math with them. Luckily, Excel spreadsheet programs of this type give us a way to do that. I'm going to say that I'm going to create a slope cell here. I'm going to create an intercept cell here. And I'm going to create a cell that contains the r squared value here. The built-in function to give us this is going to be equals slope, open parentheses, and we can see that the spreadsheet program is giving us a little hint here. It says data underscore y, comma, data underscore x, close parentheses. What this is telling us is that it wants us to choose all of the y values, enter a comma, and then choose all of the x values. What it's not telling us is that these have to be matching sets, meaning that the y cell I begin with, when I'm entering my data, needs to be the matching set to the x one, since B2 is matching up with A2, I need to begin here. I can then close my parentheses and see that it is in fact giving me a value that is consistent with this one, and I can also see that it did a fair bit of rounding here. Now, you may want to format that, and I would also like to show you what happens when you do not choose the matching set of data. For instance, what if I had dragged down when I entered the y data and instead dragged up when I did the x data? Well, it appears that this program was smart enough to correct it for me, but they won't all, and it did actually still return the correct value. So kudos to Google Sheets for that. When I want the intercept function, I'm going to hit equals. I'm going to type in intercept. I'm going to open parentheses, and it wants the exact same data. All of the y values, a comma, and then all of the x values. When I want the r squared value, I'm going to say it equals. I'm going to type in RSQ. I'm going to open the parentheses, and I'm going to feed it the exact same data. We can see that these are all consistent with what we saw from our plot. If we inspect these equations, we see that all of them had the same argument, meaning what was fed into them, B2 through B7, comma, A2 to A7. And the only thing we changed was the function we were having here, and they're named pretty reasonably. Slope for the slope, intercept for the y-intercept, and RSQ for the coefficient of determination, r squared. Now, why would I want to do this? Well, oftentimes what we're going to do in this class is we're going to vary some variable, and we're going to make measurements. We're going to know the values that we're varying down here. But later, we're going to be given an unknown. In that unknown, we are going to make a measurement of it, and graphically, we're going to determine its x value. All right, we're going to determine its x value. Graphically, the way we would do that is taking its measurement, tracking over to this line, and coming down to this line. This would be the x value that corresponded with the one that I had here. Numerically, what we're going to do is we're going to recognize that this is y equals m times x plus b. And if I want to solve for x, I need to invert that equation, meaning that I'm going to need to say that x is equal to y minus b divided by m. I'm just solving for x here when I do that. I want to input that equation in here. Well, I could do that fairly easily at this point. For instance, what if I say wanted to input 8 for y, I should return 1. Let's see if we can do that. I'm going to say that this cell equals this y here, 8, minus the intercept that I have here, divided by the slope that I have there. And I get 1.2. Why did I not get 1? Well, I didn't get 1 because what we returned is the point on the line at 8, not the point that we had before. But we do see that it's close and that this line is lying a little low here. So that means that I would have to go a little higher to get up to that 8 value. So it still makes sense and allows us a method for collecting data, assessing the quality of that data, and then being able to make predictions based on our measurements. Now we've made it to the exercises section of our laboratory. These are going to be your deliverables to me. You should complete part 1, part 2, and part 3 in your sheet, and then you're going to submit that sheet to me on Canvas. What I'm going to do, though, is I'm going to do part 1 and part 2 for you here. You can follow along at home, and then you are going to complete part 3 on your own. All of these parts need to be in your Excel sheet and then submitted to me on Canvas. Let's start with part 1 here. Hookworms. Hookworms are parasitic nematodes that live in the intestines of a host. That sounds undesirable. Hookworms do their damage, often fatally, by draining blood from the intestinal wall. The data in Table 1 correlates to the number of hookworms and the amount of blood lost caused by that number of worms. Okay, so 24 worms drained 12.2 milliliters, 5 drained 2.48 milliliters. All right. Enter the data from Table 1 into Excel. So the first thing we're going to want to do is get this data into our spreadsheet. I'm going to highlight again from the top left to the top bottom. I'm going to copy that. If we come over to our guy here, we can paste in by holding down Control and pressing V our data. I'm now going to clear the formatting for these number sections here to make a point. When I do that, we see that these are right justified, meaning it identified them as numbers, and these ones are left justified, meaning that it still thinks that they are words. This is going to be often the way that we see things when we try and do a copy and paste from a table like this that we see on something like a web page or a document. This was not formatted with a spreadsheet in mind. We cannot work with these values like this and do math. For instance, if I tried to do that, say I wanted to sum these values together, we can see that it will return a value. It didn't even give us an error in this case. It returned a value of 0 in this case. We can clearly see that the sum of these would not be 0. But in a more complicated example, this may be something that you overlook. So we have to be very careful here. We need to make sure that the program is recognizing that these are numbers. The simplest way you might think to do this is to hold down, get in there, and erase that unit, in which case it is now in fact representing it as a number. But if I had a lot of these, that might be kind of burdensome. There is another method. What I'm going to do is I'm going to highlight all of these guys here, and I'm going to come up here to data. When I click on data, I have a lot of different choices. One of them is split text to columns. Seems a little nebulous to me. I'm not sure exactly what that means. If you click on it, you can see that you get this small little pop-up right here where it says detect automatically. In my experience, if it was able to detect it automatically, it would have done it already. What it's asking you for is, what is the separator that is separating the number from the unit? In this case, what's separating the number from the unit is a space. I can come here and grab this drop down here and hit space. When I do that, what it did was separate the numbers in this column with the units in this column. Now, I can simply delete that whole column. I do need some way of indicating what the unit is that I'm working with here. The way this is typically done is by coming up here, choosing some brackets that you have not used before, for instance, square brackets, and inputting the unit in there to make it clear that these values are in fact milliliters. I'm entirely right justified now, so I'm good to move on to the next step. Remember to label each column appropriately. So we did that. Create a new column to determine the blood loss per hookworm for each data set. Blood loss per hookworm. First thing that I want you to realize is this word here, per. Anytime you hear the word per, you should be thinking about division. The blood loss per hookworm is the amount of blood loss divided by the number of worms. Why would we want that, you might ask yourself? Well, we want to know that because this data is not particularly clear to us. Why did 24 worms drain 12 milliliters while 5 worms only drained 2.5 milliliters? Is this difference due to the fact that there are more worms here? Or is something else happening? Is this case causing there to be more blood loss than in this case? The only way to do this is to get a normalized value, to figure out the blood loss per hookworm and see if it's any different in any of these cases. In order to get this, we're going to go to this cell and we're going to say that it's going to equal the blood loss divided by the number of hookworms. You can see that it has a suggested autofill here and that it is in fact doing the correct thing that I want it to do. So I'm going to hit enter here, and then I'm going to check to make sure that each of these cells is in fact doing what I wanted it to do by dividing the blood loss B7 by the number of hookworms. I can then highlight all of these go to number here and select the amount of digits that I want to see. In this case, I would like to see 2 decimal places for each of these. As a matter of fact, to see this difference, I may even need to see another additional decimal place. Now we can see that each worm is in fact consuming about a half a milliliter apiece. There is no big difference, and this is indicating to me that the likely case here is that the difference in the amount of blood loss is in fact due to the number of hookworms that we have. In order to actually make that claim, though, we're going to need to calculate the average of these values and their standard deviation. If I am in fact correct, the standard deviation should be relatively low. Let's see what the thing asks us to do next. It says report an average blood loss per hookworm and the standard deviation of the data set. In order to do that, you will make a label. Now, an important thing to do here is to make sure that we are always carrying through with our units. This is milliliters per worm. The average is going to pick up the exact same unit as the data that you are trying to average. So this is also milliliters per worm. And the standard deviation is also going to have the same units as your data. To get these values, I'll use the average function. I will highlight the blood loss. I will come down here. I will use the standard deviation, STDEV. I will highlight the exact same data. I will not include the average. And I'll close that off. We can see that this standard deviation is an order of 100 lower than the average, meaning it is relatively small. And our assumption that the blood loss per hookworm is fairly valid. What we can still do, though, is come in here and format this number into a scientific number because it's fairly small. Let's go back to our assignment and see what they asked for next. Next, report the percent error of the data given a known true value of 0.498 milliliters per worm. The equation for the percent error is this. So we need a way of entering this equation into our spreadsheet. I'm going to mention this because we will be working with the percent error quite a bit in this class. In this example, and in some other examples, we are going to be comparing the average to the actual value that we're given. It does not need to be the average. You can use the percent error formula to compare any number to a known true value. It just happens to be, in this example, we want to compare the average to the actual. In other examples, you may have something other than the average that you want to compare to a known value. Okay? These vertical lines here are indicating an absolute value, meaning that if this difference returned a positive, it stays a positive value. If this difference returns a negative number, we are going to change it to be a positive value. This always gives us positive values for the percent error. This also means that this order here does not matter. If you are appropriately using the absolute value, the actual minus the average would give you the exact same thing as the average minus the actual. In the denominator, you will always put the value that is the true value, the one that you looked up in literature, for instance. Your gold standard will always be the denominator. We then will multiply this by 100%. Some students get a little confused about this. They seem to think that the percent is an operator, like the way it operates on a calculator that has a percent button. This is a big mistake, okay? I'm not sure exactly why they ever added that button to the calculator. The percent is a unit. You're going to take two values with the same units, milliliters per worm, and subtract them. Anytime you're subtracting or adding, your numbers must have the same unit. Once you've done that subtraction, you will have a number that still has that unit, milliliters per worm. We're going to divide it by this number again that is also in the units of milliliters per worm. This means that this whole quantity here will now be a unitless ratio. When we multiply that unitless ratio times 100%, we get the percentage out. It adopts this unit from that multiplication. Let's go to Excel and see how we go about doing this. In order to make this a little clearer, I'm going to place this over here and this over here so that we can look at them side by side. I want to have the percent error, the percent error equal. Notice I didn't put a unit there. I feel that this percent here implies that this is units for this is going to be percentage. I need to input this guy over here. The first thing I always like to do when I'm looking at a ratio like this is to set up what I call the bones of the equation. I'm going to have a set of parentheses that are going to contain my numerator, a division symbol, and a set of parentheses that are going to contain my denominator. In my numerator, I want the absolute value of the average minus the actual. There is a built-in function in these spreadsheet programs for the absolute value, and it is ABS. Anything inside of these parentheses will be returned as a positive value. I now need the average minus the actual. The easiest way to make this happen is to start making a cell that contains the actual number. So we'll need to add that now. Now I can simply come back here, place my cursor inside of that absolute value function, and do the average. First I need to tell it that it's going to be an equation so that it'll allow me to do the clicky, the average minus, and it's going to hide the actual from me, but I found it. There we go, the actual. So now I have the absolute value of the average minus the actual in my numerator. In the denominator, I need the actual value. So I need to click on that guy right there. And I'm going to hit enter. Notice that I did something here. I did not do times 100%. And the reason I did that is because it's actually kind of a bad thing to do inside of a spreadsheet program. The more desirable thing to do is not to actually multiply it by 100%, but to format that cell as a percentage. This allows you and requires you to understand that you will always work with these values as if they are these ratios and not a percentage. Meaning you will not go back and take this number and divide it by 100 later to do your math, but instead treat it as if it is this value. To format it as a percentage, we come up here to format, we go to number, and we select percentage. And we can now see the percent error that we have is 0.41%. Whether or not that is a good value depends on your experiment and the criteria you've set up in advance. A good rule of thumb that I have always followed, though, is that a percent error of less than 5% is pretty darn good. And therefore we would say that this data is of high quality and that this average is well representing the middle of this data and that this standard deviation is fairly low. Well, and we've also seen that the standard deviation is fairly low. It is an important thing to note that we are actually measuring two different things with these values. The percent error is a measurement of accuracy. It's telling us how close our average, the middle tendency of our data, is to the true value, whereas the standard deviation is a measurement of precision. It is telling us how well we were able to reproduce our various measurements. Both of them are qualities that determine the overall quality of the data you generated in an experiment. Now, I have made this look pretty darn ugly. We may want to format this into something that looks better than this. There are some built-in functions that are going to help us to be able to format this to make present our data a little bit nicer to our audience. One of the first things we're going to want to do is to come up here and highlight these guys and make sure that they all have the same font and the same font size. We can bold them all. This is typically a nice thing to do with your headings. We can then come here and make sure that we move this over to be able to encompass the entire heading. After that, we can come to these two click on this little paint can here and get rid of that formatting there. It looks like it did a weird thing, so I'm just going to go to reset. And then I'm going to come here and I'm going to make the text color black. Another option would have been to just start with all of them, go format, clear all the formatting, and then select the various different things that I wanted to do with them. If we highlight the entire thing and come to format here, you can see that they have this alternating colors down here. If we click the alternating colors, it gives us some defaults for how we might want to represent these guys with nice alternating colors going up and down. You typically want to pick something like gray or blue to keep it as professional as possible. Now that is a nice looking table. I can clearly see what each of the columns represent, what their units are, and I can easily track across to be able to read. Because your professor is old, you may even want to highlight these guys here and make them a little bit larger. Now, before we move on to our next step, we want to do a couple more formatting issues. The first thing is we never gave our spreadsheet a name. If I click up here, I can add a name. A good name for this would be like Spreadsheet Lab hyphen your initials hyphen today's date. This will allow both you and me to have good information based on the file name alone. Down here, you'll see that there's a little tab that's been hiding from us with a little drop down. If I click there, I can click rename and I can rename this entire sheet Bookworms, or possibly even part 1. After that, you'll notice there's a little plus down here. If I click that, it's going to add another one of those sheets down here. This is a desirable thing to do. When you are moving to a new activity, you should place it on its own sheet. Don't make people hunt for your stuff inside of a sheet. Nobody wants to do that. Let's go back to our assignment and see what the next part is. Pi, that's the Greek symbol for pi, is the ratio of the circumference of a circle C to its diameter D. The value of this ratio is a constant regardless of the size of the circle. Thus, pi is a universal physical constant. The circumference is always going to equal pi times the diameter of the circle. The diameter and circumference of several circles were measured by chemistry students, each using a different ruler. So different people using different rulers. The first thing it wants us to do is enter these values into Excel. We have a highlighted section here that says pay attention to your units. Make sure that all values you enter have the same unit. Well, let's do our copy and paste first, and then we'll see if we can tackle this unit problem. I can clearly see that I do have a bit of an issue with the units here. What I need to do is convert these all to the same unit. In this class, we're always going to favor the metric system over the standard units. Therefore, wherever I see inches, I want to convert those values to centimeters. I can also see that I have the exact same issue that I did before. All of these numbers have been mixed in with their units, and they are now being considered words. In order to fix that, I'm going to do the same thing I did before. However, do recognize that when we did that, these units were shifted over to the column next to each other. That means that when I do it here, it's going to want to shift them over to this where there's already data entered. In order to avoid a problem in the future, I'm going to move this over to make room for these units to be shifted. So remember, I highlight them, I go to data, I go to split text along columns, I come down here. Oh, no, it already did it for me, so I don't really need to worry about that. I'm going to highlight those. I'm going to go to data. I'm going to hit split text along columns. Again, it already did it for me. I didn't need to tell them about the space, but I could have if it had been an issue. Now, I need to convert this number to centimeters. I happen to know that there are 2.54 centimeters in an inch. So anywhere where I see inches, I could just go through and multiply these numbers by 2.54. But what if I didn't know that? Well, if I didn't know that, I could use Excel's built-in convert function. I can do that by saying this equals convert, opening the parentheses, entering that value, having the comma there. I now need to tell it the unit that it's currently in. The way I need to do that is by entering a string, a word. Anytime you're going to enter in a word in a function in Excel, it has to be protected inside of parentheses. This is just a basic thing that people do all the time when they are programming. So I need to hit parentheses, inch, in, close parentheses, and then, those are quotation marks. I need to protect it inside of quotation marks, not parentheses. Then I hit the comma again, and again inside of quotation marks. I need to tell it the unit I want it to have. I'm going to do quotation marks, centimeter, quotation marks, and I'll close that all off. When I hit enter, I see that it has done that conversion for me. Is it right? Well, I was trying to convert 1.56, and I said that we needed to multiply by 2.54. So if I come down here and I say 1.56 times 2.54, I should be getting the same number. And in fact, I am. It does know how to convert for me. One thing that's nice is to make sure that we know that we already did that conversion. That's why I didn't delete this column right away, because I can now label this one centimeters. And I can come here and do the exact same thing. I can now see that I have converted all of these values to centimeters. Now would be a good time to remove these columns, place this guy back over here, and make it clear up here that I am working in centimeters. Now we have a nice homogeneous table with all of the same units, and they're all being recognized as being numbers. If you want to be sure, you can always highlight those again and make sure that they are right justified. If we go back to our assignment, we can read what the next thing is they want us to do. It says prepare an XY scatter plot of the data. Add a trend line, equation of the line, and R-squared value. Prepare cells with the slope, intercept, and R-squared values. Compare the value of your slope to the value of pi. Did you achieve the expected result? Explain your reasoning. Okay. Well, to prepare a plot, I need to start again at the top left and go down to the bottom right. I need to go Insert, Chart, and I need to make sure that I have a descriptive label up there. I do prefer this in the X versus Y type fashion. I don't know why spreadsheets always do the opposite. Any text I have ever written has always done it as X versus Y. And I see that those are labeled. Does my data make sense? Well, if we take a look at this, one of our points should have been 1.38 and 4. That looks to be about 1.38 to me, and that looks to be about 4. And the last of our points here should be 7.28 and 21, almost 22. That appears to be about 22, and that appears to be about 7.8. It seems like we did achieve what we wanted. Let's go in here and edit our chart. Remember, we need to come over to Customize, go to Series, and add our trend line. We need to be sure that we're showing our equation as well as our R-squared value. Now we have all of the information that we're looking for here. You may at times want to make sure that this is what they're calling the legend, that is placed in a different spot. For instance, on the side here, sometimes it's a little bit nicer. But for now, we're going to leave it up at the top. Now we need to make sure that we generate those cells that have the slope, the intercept, and the RSQ value. Remember that this function is slope and that it wants all of the y values, comma, all of the x values. Remember that this auto suggestion here is probably not going to be correct, so we're just going to exit out of that. It doesn't know what we're doing. I'm going to say it equals the intercept. It wants all of our y values, comma, all of our x values, and finally we want the RSQ equals RSQ. We'll open this up. We want to highlight all of our y values. We don't want the slope in there, just the values up here, comma, all of our x values. If we inspect these equations, we should be seeing that they all have the same argument, and they in fact all do. B2 to B6, comma, A2 to A6. We now want to format these values. I believe that 3 decimal places would be fairly appropriate here. Now, let's go back to our assignment. Prepare the XY plot. We did that. Trend line, R squared. We did that. Okay, cells with those values. We did that. What does it say next? Compare the value of your slope to the value of pi. Did you achieve the expected result? Explain your reasoning. Now, comparing values is the way we're always going to do that is going to be by using this percent error. Remember that even when it doesn't explicitly say it, you should always use statistics to justify your conclusion. So let's enter in here the true value. The true value of pi is 3.141592. However, I just arbitrarily stopped at 2 because those are as many digits as I know. Instead, what I should do is use one of the built-in functions of Excel. This one is called pi, Pi, and it is what we call an empty function, meaning it does not take any argument. Instead, you just type in equals pi with the empty parentheses, and it will return the value of pi. It knows the value to many, many more digits than we did, and if we formatted it so, it would show them to us. We now want to see the percent error between the true value that we know pi to have and the slope of our line here, which is our experimental version of pi. Remember that the slope is the rise divided by the run. In this case, the rise is the circumference and the run is the diameter. If we look at this equation, we'll see that the circumference divided by the diameter would be equal to pi. So we'll calculate our percent error. Remember that we tend to start with the bones of this equation. We need the absolute value at the top, and we need the difference between what we know the value to be and the experimental value that we got. We're then going to divide that by what we know the true value to be. We can now format this as a percentage. Where's percent? Right there. And we see that we got 4.46%, which I would say is pretty high but still acceptable. We're below that 5% threshold that I mentioned earlier. You can see that in this case, it's still leading to a fairly significant difference. We are about 0.14 off from the actual value, which is pretty significant given the fact that the number is relatively small. Now we can go through here, clear this formatting, and reformat these values. I'm going to make these guys 12. I'm going to bold them. I'm going to set them in the center like that. I'm going to highlight the whole thing here. I'm going to come up to format. I'm going to put in alternating colors. I'm going to pick a nice professional color tone there. And I believe we have finished that entire section. Oh, it's asking us a question here. Did you achieve the expected result? Explain your reasoning. Okay. Well, it wants us to enter in some text. The best way to enter in text into one of these guys is to highlight a block like that and then come up here and take a look at this button right here that says merge cells. entering text is about the only time you want to merge cells. It can lead to complications later. Use it wisely. If we merge those cells, we can now have an area to enter in our conclusions. We can say the percent error for the experiment was below the 5% threshold. Therefore, our results are valid and our slope is reasonably close to pi. Notice that it drops it down to the bottom like this, and we don't get to see everything inside of that text. We need to fix that. If we come up here to formatting, we can align it to the top. And then if we come to wrapping, we can wrap the text, meaning it will stop and come back around. We now have all of the things that we asked for. We have formatted this in a reasonable way that looks nice. We're answering the question, and we have a nice graphic over here that at some point got messed up. In order to fix that, we need to click here, select the range, and highlight again our values. That tends to happen sometimes, and I really am not sure why that happens. I really only notice it inside of Google Sheets, but just remember that that's the way that we fix it. You would come to the three buttons, go to Edit Chart, hit this button right here, and then re-highlight your data, again from the top left to the bottom right. We can come down here and rename this sheet. Let's take a look at the last assignment. I'm not going to do this one for you, but I am going to offer you a couple of hints. First off, we're being asked again to copy and paste this over. We do have consistent units over here. They are all in PSI, pounds per square inch. However, we do not have consistent temperature units. We're going to need to convert all of these temperature units to Celsius. That will make them consistent with the true value we're beginning down here, that is in PSI per Celsius. The other big issue we're going to have is that they use this rather vulgar way of representing a scientific number. There is simply no way to fix that simply by copying and pasting. We have to use our brains here and change this to be the number that it was intended to be. For instance, this is meant to represent 33.9. You would actually physically want to enter that value in, 33.9, as opposed to doing the copy and paste. Sometimes it's just simply not worth it. That would be the biggest issue with this one. Otherwise, it's fairly similar to the circle problem. I'm certain you guys will do just fine with it. Now, the most important thing is, how are we going to get this to Professor Stockstill? Well, as I mentioned at the beginning of this video, this is existing on a server at Google. I need to get this file onto my computer so that I can upload it to Canvas. The way you do that is by clicking File And instead of the save that you would normally have, you need to go to download. Also, just as a note, uh, it is it's always saving when you're using one of these so that you don't have to hit save. What I would like you to do is to download for me a either Microsoft Excel.xlsx. You click that, and if you're in Chrome, you're going to get something like this that shows you that file that you downloaded. I'll open it up here and move it to the side from now. I do want to mention that Google Sheets does have a built-in function to share your sheets with others. It is done through this button. I often get links from Google Docs where a person has not bothered to change the permissions of the sheet. You can see that when I put my button over it, it says private to only me. Now Google is more than happy to allow you to share this with other people, knowing that they will not be able to view it because it is private and only you can see it. If you wish to use this function, the first thing you need to do is to come in here and change those permissions. You would do that by coming down here and changing the permissions here to ensure that you're talking about whoever you want to share it with is in one of these groups. Restricted typically is only going to give people access when they have the link. Sometimes, not even then. mcc.edu is going to allow anybody with an @mcc.edu email to view your file. And anyone with the link is going to literally let anybody see it. Okay? Now, I'm sorry. Restricted won't allow anybody to do it. If it's restricted and you send them the link, they're not going to be able to open it. Anyone with the link can be able to open it with that. The person would have to be at mcc.edu in order if you had that. Now, I'm going to tell you right now that if you try to share this document with me using this share function and not uploading a file to Canvas, I will not grade it. I need you to upload it to Canvas, and in your future endeavors, there will often be times when you need to upload a file somewhere. So we've downloaded the file. We'll go back to Canvas, and you will note that there is this spreadsheet report right here. If you click on that, you will view something that looks like this. You will click Start Assignment, and you will choose a file from your computer, the one that we generated before, to put on here. You can drag and drop that if you would like. Then you'll hit Submit Assignment, and you'll get some confetti for your trouble. Okay? This will allow me to download all of the spreadsheet files at once with a reasonable naming scheme that helps me to keep it clear for all of you guys so that I can do the very best when grading them. Future labs will also require a spreadsheet assignment. Whenever a spreadsheet assignment is due for a lab, you're going to see that you'll be able to upload it directly to Canvas.